All right, so you're ready to jump into the world of econometrics, huh? It can seem a little intimidating at first, but we're here to break it all down. You guys sent us your notes from an econometrics class in this super interesting PDF, and our mission is to pull out all the good stuff without getting too bogged down in all the technical jargon, right?
Yeah, I think what's so cool about econometrics is it's this bridge between economic theory, like all those elegant models, and the real world, which is, well, a lot messier. It's about using data and statistics to test those theories and see how the economy actually
It's
works.
kind of like being an economic detective.
Exactly. You're using the data to uncover those hidden relationships, find those connections that you might not see just by looking at the surface.
I like that. So we're talking about using data and statistics to really test those economic theories. But this isn't just like a boring lecture, right? We're going to dive deep, pull out all those fascinating nuggets, and hopefully you walk away with some real aha moments.
Definitely. And, to make it even more concrete, we actually have a real world case study about housing prices. It'll make you think twice the next time you see a real estate listing, I guarantee it.
Ooh, a housing mystery. I'm already intrigued. But let's back up a bit and start with some econometrics basics. I see in your notes you've got this fundamental equation. Y equals 0 plus middle one plus BOPX2 plus fween. It looks a little bit like alphabet soup to me, honestly.
Yeah, I get it. It can be a little daunting at first, but think of it like a recipe, all right? Y is our outcome, like the thing we're trying to explain in this case, the price of a house.
Okay, so the price of a house is like our final dish.
Exactly. And the X's are our ingredients, those factors that might influence that price. Things like square footage, number of bedrooms, the neighborhood, stuff like that.
So if we're cooking up a house price, square footage and bedrooms are key ingredients. And those are coefficients. They tell us how much each ingredient matters.
Exactly. Each Maya tells us how much a change in one of our X's, our ingredients, is associated with a change in the price, our Y. So Maya Duan might tell us that for every additional square foot, a house price increases by, say, $200, assuming everything else stays the same, of course.
Wait, assuming everything else stays the same? That's what economists call ceteris paribus, right? Why is that so important?
Because in the real world, nothing ever stays the same. Everything's constantly changing. But ceteris paribus allows us to isolate the impact of one specific ingredient, like square footage, while mentally freezing all the other variables.
So it's saying, okay, let's just focus on how much square footage matters and pretend for a second that the number of bedrooms, the neighborhood, and everything else stays exactly the same.
Exactly. It's a way of simplifying things so we can really see how each ingredient contributes to the final dish, that final house price.
Got it. So ceteris paribus is our way of controlling the experiment, making sure we're not getting fooled by other factors changing at the same time. What about that little orc at the end of the equation? It looks a bit out of place.
Ah, yes, that's our error term. Think of it as the secret ingredient, all those unpredictable factors that can influence the price, but that we aren't explicitly including in our recipe.
So maybe the house has a beautiful view or it's haunted, who knows? Things that could affect the price, but that we can't easily quantify.
Exactly. It represents the inherent randomness and complexity of the real world.
The secret sauce that makes every house price unique. Makes sense. Now, I also noticed in your notes that you talk about using logarithms in these models. Why would we switch to logarithms when we already have a perfectly good equation?
Sometimes it just makes more sense to think in terms of percentage changes rather than absolute changes. Like imagine you get a $10,000 raise. Sounds amazing, right? But if you were already making $200,000 a year, that's only a 5% increase. But if you were making $50,000, that same $10,000 raise is like a 20% jump.
So the impact of that raise really depends on your starting point.
Exactly. Logarithms help us capture those percentage changes directly. So in a log model, those bank coefficients, instead of telling us how much the price changes in dollars, they tell us the percentage change in Y for a 1% change in X.
Ah, so we're thinking about things relatively rather than in fixed amounts. That makes sense, especially when dealing with things like prices, which can vary so much.
Yeah,
And this brings us to the concept of elasticity, right?
you got it. Elasticity measures how responsive one variable is to changes in another in percentage terms. And log models are super handy for estimating those elasticities.
Okay, cool. So we've got our basic recipe for an econometric model. But your notes also mentioned something called binary variables. Those sound more like something from a computer science class, honestly.
It might sound technical, but it's actually pretty simple. Binary variables are just like yes or no switches. They can only be a 0 or a 1. Like gender could be a binary variable. 1 represents female, 0 represents male.
So instead of measuring something continuous like square footage, we're dealing with categories.
Yeah.
Like either you have a fireplace or you don't.
Exactly. And these binary variables can be either our ingredients, the X's, or the outcome we're trying to explain, the Y. Let's say we're studying whether having health insurance affects people's access to healthcare. Whether or not someone's insured, that would be our binary variable.
And access to healthcare would be our outcome.
Exactly.
Interesting. Your notes actually use a similar example, the gender wage gap. It says that the Ager coefficient on gender would tell us the average wage difference between men and women.
That's right. It's a powerful way to quantify those kinds of group differences, but we can take it even further with this concept of interactions between variables.
Okay, now things are getting really interesting. So an interaction means that the impact of one ingredient, like square footage, can depend on another ingredient, like, say, number of bathrooms.
Precisely. Let's stick with the gender wage gap for a second. An interaction between gender and, say, years of experience might mean that the effective experience on wages is different for men and women.
Oh, so maybe for every additional year of experience, men get a bigger salary bump than women, or vice versa. We're trying to see if that relationship holds true across genders, right?
Exactly. That's what the interaction term lets us explore. It's those complex relationships where the effect of one variable isn't constant, but depends on the context.
So we're adding another layer of nuance to our recipe. Cool. But how do we actually figure out those coefficients? Those numbers that tell us how much each ingredient matters. It seems like a lot of guesswork.
Well, that's where a method called ordinary least squares, or OLS, comes in. It's kind of our workhorse tool for estimating those coefficients.
OLS. I vaguely remember that term from stats class, but it always sounded a bit mysterious. Can you demystify it for me?
Sure. Imagine you have a scatter plot of data points, like house prices versus square footage. OLS finds the line that gets as close as possible to all those points, kind of like finding the average trend. Of course, it gets more complicated when we have more than two variables.
Yeah, because we're dealing with like a multi-dimensional space instead of just a flat piece of paper.
Right. But the basic idea is the same. OLS is helping us find the uncoefficients that best represent the patterns in our data.
And that helps us understand those ceteris paribus relationships.
Exactly. OLS lets us isolate the effect of each variable, like holding square footage constant to see the impact of adding a bedroom. It's like a statistical microscope, letting us zoom in on those relationships, even when the real world is this big, messy jumble.
OLS sounds pretty powerful, but I know there's always a but, right? And in this case, it's that spooky-sounding omitted variable bias.
Yes. This is where things get really interesting, and it's crucial for understanding how even the best econometric analysis can go wrong if we're not careful.
And I see in the source material, you guys have this awesome example to illustrate this. It's about housing prices in Ames, Iowa. And it starts by pointing out that at first glance, houses with more bedrooms seem to sell for higher prices, which makes perfect sense, right?
It does, right? More bedrooms, more space, higher price. Seems pretty straightforward.
Yeah, that's what I would thought too. But you're saying there's a catch, like maybe more bedrooms don't always mean a higher price.
You got it. The source material points out that there are actually two ways to add a bedroom to a house. You can either build an extension, which increases the overall square footage of the house, or you can just rearrange the interior walls without changing the total size of the house at all.
Oh, I see what you mean. Like you could convert a den into a bedroom or maybe split a large bedroom into two smaller ones.
Exactly. And that's where things get a little tricky. If we just look at the relationship between the number of bedrooms and the sale price, we're not taking into account that those houses with more bedrooms might also just be, bigger overall.
Yeah, it's like comparing a tiny studio apartment to a massive mansion. The number of bedrooms isn't the only thing that's different.
Right. And that's where this omitted variable square footage comes in. It's likely correlated with both the number of bedrooms and the sale price.
So if we ignore square footage, we might think that bedrooms have a much bigger impact on price than they actually do. Like, we're giving all the credit to bedrooms when square footage is the real hero behind the scenes.
That's a great way to put it. It's like saying, wow, adding an extra bedroom added $50,000 to the price. when in reality, it might have been that extra 300 square feet that came with that bedroom that really drove up the price.
So it's omitted variable bias in action. It's like
Yep.
a hidden factor that's messing with our analysis. So to really get this right, we need to include both square footage and the number of bedrooms in our model, right?
Absolutely. We want an equation that looks like this. Price equals 0, 1 plus 0, 1 square footage plus magnitude number of bedrooms plus song. That way we can see the separate impact of each variable.
Okay, so Math 1 would tell us how much the price changes for each additional square foot, assuming the number of bedrooms stays the same. And Math 2 would tell us how much the price changes for each additional bedroom, assuming square footage stays the same.
Exactly. It's ceteris paribus coming to our rescue again, letting us isolate the effect of each variable while holding the others constant. So, what do you think happened when the researchers actually estimated this model?
Well, I'm guessing the coefficient on square footage was positive, meaning more square footage means a higher price. But what about that coefficient on bedrooms? Did it change when we added square footage to the mix?
It did. In fact, the results got really interesting. The coefficient on square footage was positive and statistically significant, just like we expected, more square footage, higher price. But the coefficient on the number of bedrooms, it actually became negative.
Wait, really? So adding a bedroom actually decreases the sale price? But that doesn't make sense. Why would anyone pay less for a house with more bedrooms?
It's a great question, and it highlights one of the key insights from econometrics. Just because two things are correlated, like more bedrooms and higher prices, doesn't mean one causes the other. There might be a hidden variable, like square footage in this case, that's actually driving that relationship.
So in this case, we're holding square footage constant, right? So if we're adding a bedroom, something else has to get smaller.
Exactly. Think about it. Maybe the other bedrooms got smaller to make room for that new one. Or maybe they had to sacrifice some living space to squeeze in another bedroom.
It's like a trade-off. You gain a bedroom, but maybe end up with a smaller living room or smaller other bedrooms.
Precisely. And it really shows why we need to be careful about jumping to conclusions based on correlations alone. Econometrics gives us the tools to dig deeper and figure out what's really going on.
It's like you said earlier, being an economic detective, you can't just look at the surface clues. You have to really investigate to uncover the truth.
Exactly.
This housing example is such a good illustration of how easy it is to misinterpret data if we're not thinking critically. We might see a pattern and think, oh, yeah, this makes sense. But there could be this whole other story hiding beneath the surface.
Absolutely, and that's what makes econometrics so valuable. It's like having a detective's toolkit for data analysis. It helps us uncover those hidden relationships, avoid those common pitfalls, and ultimately get closer to the truth.
Okay, so we've seen how omitting a key variable can really mess with our results. But I remember you mentioned something called fixed effects as a way to address this problem too. Didn't those researchers use an example comparing housing prices in Manhattan and Ames, Iowa?
They did, and it's such a great example of how fixed effects can help us control for those unobservable differences between groups that might be messing with our analysis. In this case, those groups were different cities.
Manhattan and Ames, Iowa. Talk about two completely different worlds. Their housing markets are like night and day.
Right. Imagine trying to study the relationship between square footage and price using data from both Manhattan and Ames. If we just lumped all that data together in one big model, it would be a total mess.
Because a 1,000 square foot apartment in Manhattan could cost millions, while a 1,000 square foot house in Ames might be like a fraction of that.
Exactly, and that's where fixed effects come in. They're like a statistical adjustment that accounts for those baseline differences between cities. So instead of trying to compare apples to oranges across cities, we can isolate the effect of square footage on price within each city.
So it's like we're creating separate mini models for each city so we can compare apples to apples within each market.
You got it. By including fixed effects for each city, we can control for all those unobservable differences, things like location, amenities, the overall dynamics of each housing market. That way we can see how much square footage matters within each city without those other factors muddying the waters.
That's so clever.
Yeah.
It's like using a special filter to block out all the noise and distractions so we can just focus on the signal. The true relationship between square footage and price.
Exactly. And the cool thing is it's actually pretty easy to do this in R using that fields function we talked about earlier.
Yeah.
You simply add the fixed effects to the formula using a vertical bar.
So in this case, we'd have a fixed effect for Manhattan and a fixed effect for Ames.
Exactly. And those fixed effects would capture all those unobservable differences that we talked about, allowing us to focus on the impact of square footage within each city. It's a really powerful tool for dealing with potential omitted variable bias and getting a cleaner picture of what's driving that relationship.
Okay, I'm starting to see how fixed effects can be a real game changer in econometrics. We can control for all sorts of hidden factors that might be distorting our results.
Exactly. It's all about being aware of those potential biases and then using the right tools to address them.
Now, before we move on to statistical inference, I remember we touched on another potential challenge, heteroskedasticity.
Yeah.
And you said that can mess with our statistical analysis too, right?
Yes. And it's one of those terms that sounds super complicated, but is actually pretty intuitive once you break it down.
Okay, break it down for me. What is heteroskedasticity and why should we care about it? All right, so heteroskedasticity. It sounds pretty intimidating, I have to admit.
It does, doesn't it? But it's really not that bad once you get the hang of it. Remember that error term we talked about, the OS in our equation?
The one that represents all those random factors that can affect the outcome, like the stuff we can't perfectly capture in our model.
Exactly. Well, heteroskedasticity basically means that the variance of those errors, like how spread out they are, isn't constant across all our observations.
So instead of those errors being like a nice, consistent sprinkle of randomness, it's more like some parts of our data have a light dusting of errors, while other parts have like a whole blizzard of randomness.
That's a great way to visualize it. And you might be thinking, okay, but why does that even matter? Well, it turns out that those inconsistent errors can mess with our statistical analysis, particularly when we're trying to figure out if our results are statistically significant.
Ah, statistical significance. That's where we get into confidence intervals, p-values, all that fun stuff.
Exactly. It's all about figuring out how much we can trust our findings and whether they hold up beyond our specific data set. But a lot of those tests rely on the assumption that our errors are, well behaved, with a consistent variance. When heteroskedasticity comes along and throws a wrench into things, it can make our results a little less reliable.
Okay, so heteroskedasticity is kind of like a red flag. It's telling us, hey, double check your analysis, make sure you're not being misled by these wonky errors. But luckily, I think you said it, our trusty feels function can handle this too.
It can. Feels has this handy-dandy argument called VCOV that lets us adjust our standard errors to account for heteroskedasticity. It's like we're telling Feels, hey, the errors are being a bit mischievous here, so please adjust the calculations accordingly.
So we're giving our statistical microscope a little tune-up to make sure we're getting a clear picture, even when the errors are being a bit fuzzy. I like it.
It's all about having the right tools, right? And speaking of tools, I think it's time to finally dive into those concepts of statistical inference you mentioned. Confidence intervals, p-values, hypothesis testing. It's all about making sure we're interpreting our results correctly.
Okay, let's do it. I have to admit, those concepts have always been a little fuzzy for me. Like, I get the general idea, but I'd love to really understand the intuition behind them.
Absolutely. And it all starts with this idea that when we do an econometric analysis, we're using a sample of data to make inferences about a much larger population. It's like trying to understand the entire ocean by studying a single bucket of seawater.
Okay, I can see that.
Yeah.
We can't possibly study every single house in the U.S. to figure out how square footage affects price, so we take a sample of houses and use that to draw conclusions about the broader market.
Exactly. But we need to acknowledge that our sample might not perfectly represent the entire population. There's always going to be some degree of uncertainty. And that's where confidence intervals come in. They give us a range of plausible values for that true population parameter we're trying to estimate.
So instead of saying the effect of square footage on price is exactly $150 per square foot, we'd say we're 95% confident that the true effect is somewhere between $140 and $160 per square foot or something like that.
You got it. That range of values, that confidence interval, is capturing the uncertainty inherent in our estimation process. And that level of confidence, usually 95%, tells us how sure we are that the true value falls within that range. It's like saying, we're pretty darn sure the true effect is somewhere in this ballpark, but we can't say for certain what the exact value is.
Okay, so a wider confidence interval means more uncertainty, while a narrower interval means we're more precise in our estimate. But how do we actually figure out those ranges? I feel like there must be some crazy calculations going on behind the scenes.
There are some calculations involved, but the concept's actually pretty simple. We start with our estimated VART coefficient and its standard error. Remember, the standard error tells us how much our estimate might bounce around if we collected different samples of data.
Right, smaller standard errors mean our estimates are more precise, And we can be more confident in our findings.
Exactly. To construct that confidence interval, we basically take our estimate and add and subtract a certain multiple of the standard error. That multiple depends on the level of confidence we want. For a 95% confidence interval, it's roughly 1.96.
So the wider the standard error, the wider our confidence interval, which makes sense. If our estimate's bouncing around a lot, we need a wider range to capture that uncertainty. But what about p-values? They always seem to be lurking around these discussions about statistical significance.
P-values are closely tied to confidence intervals. They're helping us assess the strength of the evidence against a particular hypothesis.
So for example, we might start with the hypothesis that there's absolutely no relationship between square footage and price. Like the true bot coefficient is 0.
Exactly. That's called our null hypothesis. And the p-value is telling us the probability of observing our estimated Burke coefficient, or an even more extreme value if that null hypothesis were actually true.
Okay, so if the p-value is really small, it means it's super unlikely we would have gotten those results if there were truly no relationship between square footage and price.
Exactly. Typically, if the p-value is below 0.05, meaning there's less than a 5% chance of getting our result if the null hypothesis were true, we reject the null hypothesis. We say, okay, we have enough evidence to conclude there's probably a real relationship here.
So it's like we're putting the null hypothesis on trial, and
Yeah.
we're saying, hey, the evidence against you is just too strong. We're finding you guilty of being false.
I like that. It's like a statistical courtroom drama. But it's important to remember that even if we reject the null hypothesis, it doesn't mean we've proven our alternative hypothesis with absolute certainty. There's always a chance we could be wrong.
Right. It's all about probabilities and weighing the evidence. It's not a smoking gun, but it's pretty convincing. But what if that p-value is above that 0.05 threshold? Does that mean there's no relationship there at all?
Not necessarily. It just means we don't have enough evidence to confidently reject that null hypothesis. There might still be a relationship there, but our data just isn't strong enough to confirm it. Maybe our sample size is too small, or there's too much noise in the data. It's like a not guilty verdict. It doesn't necessarily mean the defendant is innocent, just means there wasn't enough evidence to convict.
I get it. And it's an important reminder that statistical significance isn't the only thing we should be looking at. We need to consider the context, the economic theory behind it, and all those other factors to really understand what our results are telling us.
Exactly. It's not just about the numbers, it's about the story those numbers are telling us.
Speaking of stories, this whole deep dive into econometrics has been fascinating. I feel like I have this whole new set of tools for understanding data, spotting those potential pitfalls, and making sense of the results. What started as a jumble of equations and Greek letters now feels like a powerful way to unlock some of the secrets of the economy.
That's what we were hoping for. It's about making econometrics accessible and hopefully even a little bit fun.
Mission accomplished.
Yeah.
But this is just the beginning, right? There's a whole world of econometric techniques and applications out there.
Absolutely. And it's a constantly evolving field with new methods and new data sources emerging all the time. It's an exciting time to be an economic detective.
So for our listener who's been on this journey with us through the world of econometrics, what's a one key takeaway you want them to walk away with?
I think it's this. Data can be incredibly powerful, but it can also be misleading if we're not careful. Econometrics gives us the tools to think critically about data, to identify those potential biases, and to draw meaningful conclusions from the information we have. So the next time you see a statistic in the news or in a research paper, don't just take it at face value. Use your econometric lens to see the bigger picture.
That's such great advice. And for our listeners who are feeling inspired to learn more, what are some resources you recommend?
Well, the source material you guys provided is a great place to start. It has some really helpful links to other resources. There are also tons of fantastic introductory econometrics textbooks and online courses out there that can really help solidify those concepts. And of course, you can always learn a lot from exploring real-world examples and case studies like that housing price puzzle we talked about earlier.
That's a wrap for our deep dive into the fascinating world of econometrics. Until next time, keep asking those curious questions and never stop exploring the data that surrounds us. All right, let's dive into heteroscedasticity. Ready to conquer this beast?
It sounds a lot scarier than it actually is. Remember that error term we talked about?
Yeah.
The all in our equation?
The one that captures all that randomness,
Yeah.
the stuff we can't perfectly account for in the model.
Yeah, exactly. Well, heteroscedasticity just means that the variance of those errors, like how spread out they are, isn't consistent across all of our observations.
So instead of the errors being nice and evenly distributed, it's more like some areas have just a sprinkle of errors while others have a whole downpour.
A perfect analogy. And you might be thinking, okay, so what? Why should I care about that? Well, it turns out that having those inconsistent errors can really mess with our statistical analysis, especially when we're trying to figure out whether our results are statistically significant.
Ah, statistical significance. That's where those confidence intervals and p-values come in, right?
You got it. We're talking about how much we can trust our findings, whether they hold up beyond just our little sample of data. A lot of those tests rely on the assumption that our errors are, well, well behaved, you know, nice and consistent. Heteroscedasticity throws a wrench in things and can make those results less reliable.
Heteroscedasticity is like a warning sign, telling us to double-check our analysis and make sure we're not being fooled by wonky errors. But didn't you say feels can help with that?
It can. Fields has a super useful argument called VCOV, which allows us to adjust for heteroscedasticity. It's like we're telling Fields, hey, those errors are being a bit mischievous, so can you please adjust those calculations for us?
It's like we're recalibrating our statistical microscope to see clearly, even with all that fuzziness from the errors.
Exactly. And speaking of seeing things clearly, I think it's time to jump into those concepts of statistical inference you mentioned, confidence intervals, p-values, hypothesis testing, making sure we are interpreting our results the right way.
Yes, let's do it. Honestly, those concepts have always seemed a little mysterious to me. I kind of get the idea, but I'd love to really understand the intuition behind them.
Absolutely. It all starts with understanding that when we're doing econometric analysis, we're working with a sample of data to try to say something about a larger population, like trying to understand the ocean by looking at just one bucket of water.
Okay, that makes sense. I mean, we can't analyze every house in the U.S. to figure out how square footage affects price.
Mm.
So we have to take a sample and use that to draw conclusions about the broader housing market.
Exactly. But we also need to acknowledge that our sample might not perfectly represent the entire population. There's always going to be some uncertainty, and that's where confidence intervals come in. They give us a range of plausible values for that true population parameter we're trying to estimate.
So instead of saying the effective square footage on price is exactly $150 per square foot, we might say we're 95% confident that the true effect is somewhere between $140 and $160 per square foot.
Exactly. That confidence interval, that range of values, is how we capture that uncertainty that's inherent in estimation. That confidence level, usually 95%, tells us how sure we are that the true value falls within that range. It's like saying, we're pretty darn certain the true effect is somewhere in here, but we can't be 100% sure of the exact value.
Okay, so a wider confidence interval basically means we're more uncertain. A narrower one means we're more precise. But how do we figure out those ranges? I feel like there's some crazy calculations going on behind the scenes.
There are calculations, but the concept is actually pretty simple. We start with our estimated beta coefficient, right? And then it's standard error. Remember that the standard error tells us how much our estimate might jump around if we had different samples of data.
Right. Smaller standard errors, more precise estimate, more confident in our findings.
Exactly. To make the confidence interval, we take our estimate and we add and subtract a certain multiple of the standard error. The size of that multiple depends on the level of confidence we're looking for. For a 95% confidence interval, it's about 1.96.
So wider standard errors lead to wider confidence intervals. Makes sense. If the estimate is bouncing around a lot, we need a wider range to capture that. Okay, what about p-values? I feel like those are always hanging around when we're talking about statistical significance.
P-values are super connected to confidence intervals. They're helping us figure out how strong the evidence is against a particular hypothesis.
So, like, we might start with the hypothesis that there is absolutely no relationship between square footage and price, that the true beta coefficient is 0.
Exactly. That's our null hypothesis. The p-value tells us the probability of seeing our estimated beta or one even further away from 0 if that null hypothesis were actually true.
So if the p-value is tiny, that means it would be super unlikely to get our results if there was really no relationship between the variables.
Exactly. The standard cutoff is 0.05. So if our p-value is less than that, which means there's less than a 5% chance of getting our result if the null hypothesis is true, we reject the null hypothesis. We say, okay, there's enough evidence here to conclude that there probably is a real relationship.
So it's like we're putting the null hypothesis on trial, and we're saying the evidence is just too strong, we're finding you guilty of being false.
I love that analogy. But remember, even if we reject the null hypothesis, it doesn't mean we've proven our alternative hypothesis with absolute certainty. There's always that tiny chance we could be wrong.
Right, it's all about probabilities and weighing the
Yeah.
evidence. Okay, but what if our p-value is above that 0.05 cutoff? Does that mean there's no relationship?
Not necessarily. It just means that we don't have enough evidence to be really confident in rejecting the null hypothesis. Maybe the relationship is there, but our data isn't strong enough to say for sure. Maybe our sample size is too small or there's too much noise in the data. Like with a not guilty verdict, it doesn't necessarily mean they're innocent, just not enough evidence for a conviction.
Yeah, that's a great way to put it. It's a good reminder that statistical significance isn't the only thing we should be looking at. We need to think about the context, the economic theory behind it, and all the other factors that help us understand the results.
You got it. Econometrics is more than just the numbers. It's about the story those numbers are telling.
And this deep dive into econometrics has been quite the story. I feel like I've learned so much. A whole new toolkit for understanding data, seeing the potential issues, and interpreting those results. What started as a jumble of equations and Greek symbols now feels like this powerful way to really understand how the economy works.
I'm glad to hear that. That's what we're going for, to make econometrics accessible and hopefully even a little bit fun.
Well, I think you definitely succeeded. So for our listeners, those econometric explorers out there, what's the key message you want them to take away from all of this?
It's this. Data can be incredibly powerful, but it can also be misleading. Econometrics gives us the tools to think critically about that data, to identify potential biases, and draw meaningful conclusions. So the next time you encounter a statistic, whether it's in the news or a research paper, don't just take it at face value. Put on your econometric glasses and look for the bigger picture.
Great advice. And for those listeners who are eager to learn more, what are some good resources you'd recommend?
Well, the source material you shared had some really useful links. You can also find some great introductory econometrics textbooks or even online courses that can help solidify these ideas. And of course, you can always learn a ton from exploring real-world examples and case studies, like that housing market mystery we discussed earlier.
That about wraps up our deep dive into the world of econometrics. Until next time, keep those curious minds working and never stop exploring the data that's all around us.